Thank you, David. Like he said, I work at Sungevity right here in Oakland, and what I've been working on is API design in Scala, interacting with Sungevity systems and building a solar platform. And the title of this talk is Functional Domain Modeling Beyond Buzzword-Compliance, and I chose that tagline because a prominent member of the Scala community, who shall remain nameless, once asked me, so is functional just the word we put in front of all the book titles we've sold already so we can sell a new version? I think no, the answer is no. That actually there's a deep connection between functionalism and domain modeling, and it's something I was pleased to discover in the process of actually working on a practical project for Sungevity. So, okay, what are we talking about? Functional domain modeling is making functional code correspond to real meaning in a language that programmers share with other people. And what I mean by real meaning, before you ask, is something that obtains in the minds of people with domain knowledge. And one legitimate question you might have about this is why? Why bother? It is more difficult than not doing it, right? And the answer is really about complexity and accuracy. At Sungevity, we needed to tell a simple but accurate and true story to each customer about their interaction with a very complicated problem. And my particular situation in developing an API was taking a stateful and not type-checked situation and turning it into a type-checked API based on immutable build-up. I'm bringing down the house already. So customers don't need or want to know about the complexity of their situation. Various jurisdictions, taxes, utilities, we operate in multiple countries, we use multiple funding partners, etc. We need to do all that stuff and account for all of those important differences rigorously, but without having to tell a story that's too complicated on its surface. And to explain our business, and I swear this isn't just an advertisement for Sungevity, but it's explaining the project. This is the simple value proposition we provide. It's called the story of SPUN, or solar for universal need. Sungevity looks at your home, it designs a system, estimates how much that system is going to cost and how much electricity it'll produce, and then shows you your savings over 20 years. And then we put it on your roof and provide you with access to your installation's performance and design information. This is our core value proposition, no matter who we're working with. And telling this story simply and rigorously and reliably for each customer at scale means accounting for a lot of complexity that nobody wants to think about in the sales process through domain modeling. So that's why we chose to do it. Domain modeling in software is the practice of making code correspond to a ubiquitous language that's shared between domain experts and programmers. You may be familiar with this from the Evans book. And ideas about members of that ubiquitous language come from both the domain experts, a subset of their knowledge, and also from the implementation process. And it's been well explored in stateful, object-oriented situations, but what I'm talking about today is how it's compatible with functional approaches. I don't know if anyone saw Chris Richardson's talk yesterday about event sourcing. Yes? Okay, a few people. And also Michael Slynn talked a little bit about using caching to build up immutable models in Play. And both of those are very interesting directions. And I'll talk a little bit more about them at the end. So how is it that they're compatible? Well, for one thing, as a historical note, functional domain modeling may actually be the original kind of domain modeling. The word domain comes from semantic domain. And in linguistics, a semantic domain is a set of concepts that are grouped by having something in common or some kind of natural category, like types of snow, chess moves, musical notes, etc. But in computer science, the idea is associated with creating a mathematical object used for rigorously assigning meaning to programs in denotational semantics, which is a semantics of programs that's compositional, assigning meaning to programs by assigning meaning to their parts. A man named Dana Scott was working on denotational semantics expressed in lambda calculus when he formalized one influential concept of domain in computer science, which is now called the Scott domain. And this was all the way back in the 1970s. And at the time, untyped lambda calculus didn't have a mathematical model relating it to functions, so he came up with one. And Scott domains are the result, or one formalization. And they provide a general semantic model for recursive programs that accounts for, recursive functions, functions that take functions as arguments. And they model it in the ordered set as a series of successive approximations building toward a result. But for our purposes, I'm not going to get it too deeply into the mathematical side, which I'm still learning about as well. It's enough to think of these sets, the domains as sets, and then products built up from sets approximating an end state. And so the reason I think I can back up this idea is that functional languages like Scala or Lisp deliberately were inspired, or they're associated with approaches like lambda calculus, which is also being used for denotational semantics. So my assertion is that functional domain modeling is actually the OG domain modeling. That there's every reason to believe that domain modeling is useful because of this sort of compositional approach, and it allows you to communicate about the real world, and that also help you meaningfully explain your code base in relation to your specific problem. And not only is it compatible with functionalism, it actually has functional origins. It's not a coincidence that as we're trying to make code more comprehensible, we take functional approaches. So, okay, that out of the way. I'm going to be talking about a toy solar domain that mirrors the API that I worked on. And it's the domain of utility consumption sites. And why utility consumption sites instead of just houses? The reason is the thing on the left is a utility consumption site, and the thing on the right is not. And at Sungevity, we're only just dipping our toe into battery solutions. So we're concerned with utility consumption sites, people who have grid. So going back to our core value proposition, this is the domain that we need to interact with customers in. I'm just going to camel case some nouns and use these as the primitives of building up our domain and some of the products. So Sungevity looks at your utility consumption site, creates a system design, calculates a system price and your production estimate, and gives you a quote that shows your savings. Then we provide you access to installation, showing a system design and performance information about your utility consumption site, which is now also a solar production site. So we can just imagine these as the domain core models in our system. And what these are a set of overlapping categories. And I hope that you can actually see that a little bit. Everything is utility consumption site. Some of those have system designs, some of those have system prices, some of those have production estimates and they're priced and estimated, and when they have the savings calculation completed, they're quotes. And so the API can mirror this structure, and when we interact with certain endpoints, we are taking a journey through this buildup of values. So the first route on the bottom there is from point A to point B, adding a system design to a utility consumption site, and then calculating the quote result, which can happen in one of two orders. We have an opportunity for parallelism. And then another one is a post of a solar production site to a quote to actually turn it into an installation. I've omitted the part where people pay us money because it's complicated. So this is a simple version of what's really going on. And so if we consider these sorts of primitives and build-ups as a grammar, we can see that there's going to be some intermediate results that we're interested in representing. And we could almost parse our story of fun with something like this. Like, we really are trying to build a language of sorts that makes sense to people who are domain users. And we can see that quote and installation are separate. They don't contain everything that the other contains. But if we wanted to imagine what is the element that contains all of the information in this system, it would be this unit, the story of quote becoming an installation. Unit, solar for universal need unit. Sorry, I love acronyms, but not everyone does. Okay, so if we were to label all of the intersections here, all of the buildups, we would see, imagining these as just products, some of the intermediate representations that we might need to be interested in as we're approaching the quote or as we're constructing installations. And then the unit at the top would be ultimately the product of everything. So this is a pretty simple algebraic situation. So not a lot of complicated understanding is necessary. So we can then translate this sort of grammatical approach into a state machine that clearly reflects the workflow. We start with a utility consumption site, then we design something, and we arrive at the second state. Then in either order, we can price and estimate and arrive at the priced and estimated state through composition. Then we calculate savings, and then we have a quote, and then eventually we install a system. And we drop some information moving into that state. And so these are the routes I'll be talking about. Getting a utility consumption site, just accessing them. Posting a system design and getting back a quote. Posting a solar production site and generating an installation. And so we can imagine these as functions between domain and codomain that are defined in terms of either basic semantic domains or their products. So again, here's a state machine representing what happens when you would post a system design and get back an installation. Or sorry, get back a quote. And if you can't read my handwriting, I'm sorry. And here's what would happen when we post a installation and post a solar production site and get back an installation. We forget some things. We add in the solar production site and get back the installation, something in the installation domain. So so far we've been talking entirely about the conceptual structure, and that's intentional on my part. I want to emphasize that I'm starting from an idea of what is the conceptual structure that we want to model. But now, of course, we have to actually put some Scala code on the screen. So here we are. So when we want to realize these models in code, there's more than one way we can do it. I did it in this example in my real API project through a system of trait buildup. But I want to emphasize that that's not the only way you could represent the product of these domains. Another way to do it would be through more ADT-style case classes and type classes. And that's something I want to explore as well. But here we can see what we've got is a case class, utility consumption site. It has an ID, address, usage, and the key information is their price. So from here we can make the basis of our calculation for how much the customer is spending. And here we have a system design case class, which is really simple. It just has a number of panels and a number of kilowatts kilowatt hours that panel is going to produce over its lifetime. Here's the system price. Again, the real domain is a lot more complicated, but we can see this is basically all we would need to calculate system price based on a system design. Here's a production estimate. Here's a savings trait. And this would be like the net savings, and the electricity savings is how much you would save immediately off of your bill, and the net savings is taking into account the cost of the system over time. And so a way of imagining their intersection is this priced and estimated utility consumption site trait, right? And this is one of these intermediate representations, and so it sounds pretty complicated, but really it's just this. It's just this node here that exists right before savings can be applied. And here's another intermediate result we might be interested in. We might want to be able to look at utility consumption sites and without knowledge of, or rather, we might want to be able to design systems without knowledge of the utility consumption site. And so the least upper bound of just the system design, the system price, and the production estimate can give us a system that's very interesting even without might be a separate aggregate at some point, right? Even without knowledge completely of the consumption site itself. And once we get to a quote, what we can see is the product expressed as a trait that has all of the information built up into it. And this is the kind of data we can use to power the API. Here's an installation reflecting all of the products that it is part of. So those are how the models are structured. And services that I created provide transitions between the traits, so new traits that take work, and then those traits can be composed onto the models to provide to actually do the work of building up the data. So here's a production estimation service. It shows a method taking a system design trait and producing a future production estimate. So we're mapping into a future of the domain, the trait that we want to compose into the model. And crucially, this only depends on satisfaction of the system design trait. It doesn't depend on anything extraneous. It's based entirely on, its requirements are based entirely on things it actually requires, and its output is only things it knows about. Similarly, here's a pricing service. Sorry for the lack of syntax highlighting here. But what you can see is there's two methods, system design to system price, which just looks up the price per panel and calculates the price, and calculating a savings is also here. And so these can be expressed and given functional denotations, or sort of loose denotations, as to what they provide in terms of the domain. So what's nice is that when we get to actually writing the model method or action for applying a system design and getting back a quote, we can do it in one for comprehension like this. So all we have to do is find our utility consumption site, get the price, get the estimate. Those two things can happen in any order. Then once we have our priced and estimated site composed, we can add on savings and return the quote. And so what's nice about this is that the structure of our for comprehension directly mirrors the kind of state machine that we constructed just by thinking about the domain concepts. So here it is. Are people's eyes glazing over? Basically, what's nice is just that it's totally parallel. And that we have a real explanation in terms of functions over domains as to what we're doing. So what does this actually look like? The thing that we use to, or the format we use to represent these entities in the API is called Siren. It's an extension of JSON that provides a set of classes describing a bunch of properties. And it has some other interesting things about it too. But for our purposes now, what's interesting is that it can provide intersecting classes analogous to trait mixins to describe what set of properties is present in a resource. So here's a utility consumption site. This is what you would post, or this is what you would get back or see as a resource when there is no system design present. And here is after adding a system design what we would achieve. Something that describes itself as a quote, a system design, a utility consumption site, a system price, a savings, a production estimate, and all of the fields therein are contained. And so just as some context for the real project I was working on here, this allowed type checking both in validation at the time of receiving the entity and instantiating types of what had previously been a totally mutable state process. It had been values that were all optional and got filled in over time as we acquired more information. And so adding into a functional immutable build-up model allowed us to have a lot better checking of what was going on during the buildup of the result. And we can write tests that say, any entity that contains a certain siren class ought to have these properties and so on. And we can base contracts on that. So similarly, here we are applying the solar production site to a quote in order to get an installation. And this is just a matter of a function from solar production site to installation in this service, or in the model, rather. So we're finding a quote and then composing the solar production site onto it and achieving the installation, like so. And that's all that a solar production site looks like, just a performance ID. And here's what we end up with as an entity for installation, describing itself with classes and showing all of the fields that is mixed together. So I would argue that, we've done some of what we set out to do, or I did some of what I set out to do. A loose semantics and a denotational understanding of the code, not a perfect one, but real meaningful anchor points between the operation of the API and semantic domains. And now the program and its programmers can communicate more effectively about how representations are composed. And we can contribute back some of those intermediate representations as meaningful categories. And we also have built up some positive reason to believe that it's correct for the whole domain and not just tests. But there's a lot of other things we can talk about. So persistence is one, and managing events, modeling events. This is also just talking about a RESTful interaction. What about other types of more reactive designs? How is that serialization achieved? And no, it's not really mathematical proof of anything because we've not done any kind of complete denotation. Some of the next steps I want to try are some more ADT style classes and using type classes for service signatures instead of trace. I think that might be an interesting approach. Event sourcing is also very interesting in that it models the entire persistence solution as a successive application of events. So not only would we be building up stuff over time, like the entire model would be built out of successive application and be approximating some immutable final result. So like even in the example of a bank account, like you can view the successive application of events as an approximation of the final immutable state of that account, that complete story of why your balance is what it is. I think it's very interesting. And certainly I'm very interested in learning more about semantic domains and techniques associated with them. And if you have an interest in this topic, I would love to hear from you. So here's some of the references, and I don't know, do we have time for a short demo? Maybe? Okay. So just to prove to you that this actually works. Where am I? So I'm just running my SBT project. Oops. And let's see if I can find that. Oops. Sorry, I got stuck in full screen. Well, while I'm fiddling around, does anyone have any questions or comments, feedback? Yes, in the back. So he asked, do I specify domain models? Domain laws. Right. And do I model functional states? Yes. Okay. So let me just show some code. The composition, these basic traits represent models of the domain, immutable ones. And the composition functions, which are pretty unsophisticated, just represent what transitions that element is capable of. Oh, not on the screen. Yeah. So, so a very simple kind of application of an event to this quote is a transition as installation, like so. And that represents the possibility of doing this. Now, there could be much more sophisticated ways of doing this. We could imagine the aggregate as something that we can do some kind of monadic application to, or each event, such as a pricing event or an installation event, as being something we can apply to the model as we go forward, like even as we're recovering it from an event store. But in a primitive sort of way here, I've got my immutable model of a certain category, and I've got the function that composes it onto it, and I've got services providing functions that are futures of things that take work to arrive at some trait that I need to compose onto the model. Yeah, good question, thank you. So let me see if I can show you. Oh, I think maybe I'm coming up against the end of time here. So trust me when I say yes, if I post a system design, I get back a quote, just in those formats that I showed you. Any last questions? No? All right, thank you.